Hi again everyone, Chris Tisdell here. In this presentation I'm going to continue my series of videos that give a gentle introduction to vectors. Now in previous videos we talked about lines and ways of representing lines through different forms of equations, the parametric vector form and the Cartesian form. And in this presentation I'm going to discuss an example to highlight the ideas. So let me share my screen with you and we'll get down to business. Okay, so here is the example that we're going to look at. We've got a vector parametric form of a line L given by this here, and we're asked to do two things. We're asked to determine a Cartesian form for L, and secondly we're asked whether or not the following point lies on L and why not. Okay, so let's quickly have a look at what we did in previous presentations. In three-dimensional space, we can have a parametric vector form involving this type of column vector for the points on the line. A is a position vector of a point on the line with these coordinates, and V is a vector parallel to the line, and lambda here is just a real number, and it's the parameter. Now this is a parametric vector form for the line L, and the Cartesian form is the following. Okay, strictly speaking, you cover up this equals lambda, and the A1, A2, A3 are just the coordinates of the point A that lies on the line, and the V1, V2, V3 are the coordinates of the vector V. Okay, now essentially if you know this vector and this vector, then you can easily write down the Cartesian form. Well, in this case the A1 would be -2, A2 would be -5, A3 would be 7, and V1 would be 4, V2 would be 6, and V3 would be -3. Okay, so it's pretty easy to write that down once you get once you realise that this is the vector position vector of A, and this is the vector V. Okay. All right. So A, -5 is a point on L with position vector OA. You just take this and write it as a column vector. Okay. Also, V, which is just this vector here, is a vector that is parallel to the line L. Thus, a Cartesian form for L is, well, it's going back to here. Let me see if I can squeeze it in. X minus A1 on V1 equals Y minus A2 on V2 equals Z minus A3 on V3. Okay, now we don't usually cover that up. I just like putting in there. We don't usually put this in. I like to, you can cover it up if you want to. I just like to keep it there so when you're going between the two, it's easy to do so. Okay. Okay, so if we write that down, x minus minus 2, which is x plus 2, all over 4. Y minus minus 5, y plus 5, all over 6. and z minus 7 all over negative 3. Okay, I know my z's and 3's look alike. That's just the way I do them. So let's put some bright colors around that answer, and that's the first part. Now the second part is, does the point 18, 25, 10 lie on the line L, and why not? Okay, so what we would like to do in solving this is to actually put this value into here, put this value into here, and put this value into here for x, y, and z respectively, and actually see if all our three parts are equal. If they're all equal, then this holds and this point does lie on the line. If one of them is not equal to the other ones, then the point does not lie on the line. Okay, so let's consider the point x, y, z with x equals 18, y equals 25, and z equals 10. Okay, so let's consider the following. So we're going to have 18 plus 2 on 4, so that'll be 5. 25 plus 5 all over 6, which is 5. Okay, so they're equal. And finally, 10 minus 7 all over negative 3. Okay, so that's going to be negative 1. Now, since this is not equal to these two things, the point cannot lie on the line. So since our values are not all equal, the point cannot lie on L. All right, I've just squeezed it in there. All right, so that's a pretty simple question. You can, if you didn't have this form, it'd probably take you a little bit longer to actually solve the second part, because you'd actually have to go through and find a lambda, or see if a lambda existed, such that 18, 25, 10 equals this plus lambda times that for some lambda. Okay, so that's one advantage of having the Cartesian form. All right, so our conclusion is this. Okay, so that's a basic example trying to illustrate the basic properties of the different forms of lines in three-dimensional spaces. So please join me again for more examples, more videos in the future, where I'll continue my look at vectors. And if you have any suggestions, any comments, please put them in the comment section below. Thanks for watching, and join me for the next presentation.